In this video, I want to talk about projectile motion. Specifically, I want to look at a couple of very common types of questions. And those would be where we have some projectile, and in this case, we're going to look at the common example where it'll all happen along some level ground. So we'll start at one height and we're going to end at that exact same height. So three types of very common questions are going to be, well, how much time does the projectile spend in the air, and how far does it go, what is the range, and at what maximum height does it reach? And so very often we're going to be looking at some combination of factors that lead you to an answer for one of these questions. And in this example, we're going to be considering three different angles where there'll be the same launch velocity. So, and I've color coded them. So we've got an example here in the orange where we've got quite a steep angle. And then we've got an example here, which will be midway. Actually, this will be 45 degrees. And then we'll have a final example of a fairly shallow angle. And so I've color coded them orange, blue, and green. Down here, I've also made an immediate note that the velocities are all going to be the same. So there's only one launch velocity. What we're going to change is this angle and see how that impacts all these quantities. The other important aspect here that I want to set out is that upwards is positive and to the right is positive. So it's important that we track what our directions are associated with. And related to this, I've also specified that when I say g for the acceleration due to gravity, which is downwards, I'm representing downwards with the negative, corresponding to that upwards is positive. This is not always the way that it's written. Very often g can be just 9.8 meters per second, leaving the negative sign to be carried some other way. I think this is more clear, but keep in mind that you will see it either way. Okay, I'm actually going to set out my specific angles. So the steep angle is 75 degrees, the midway, the blue, is 45, and the shallow is 30. So before we carry on into one of the calculations, I want to quickly note a couple of things about projectile motion. So I'm just going to write a quick bit of note here. I'm going to say, just note as we begin that our x and our y motion are independent. But they are linked in time. But they are linked by time. In projectile motion questions, we're very often going to look at what's going on in the x direction and look at what's going on in the y direction, and the link between the two is time. Now, what's going on in each of these? Well, in the x direction, for projectile motion, by definition, once it is launched, nothing else is going to happen to that object aside from the presence of gravity. So in the x direction, there exists no acceleration. Now this is assuming no air resistance. Let's say assume no air resistance. And that's a reasonable model for some cases. Okay, so that means in the x direction, what we have is constant speed. Okay, now in the y direction, there's more going on. So we've got in the y direction, there exists acceleration. There exists acceleration in the y direction due to gravity. And that we represent with little g. Okay, so in the y direction, the other way that we can relate this to other concepts that we've talked about, this is like, in fact it is identical to, is like 1D motion of an object that's thrown straight up. And we're going to come back to this link and this idea of that relationship between the y component motion in projectile motion and that kind of 1D thrown in the air motion, and the fact that that's exactly what's happening in the y direction. We're going to come back to that when we start to work through projectile motion more mathematically. Okay, so that sets out some of the important concepts around projectile motion as we get into it. So as we are going to be talking about the x and the y, just wanted to do a little reminder that when we're looking at these vectors, we are going to have, if we were looking at the blue one here or any of them, you can break that down into your x and your y components, and we'll be doing a lot of that. And you see this drawn out here where we've got our velocity vector, and using the angle we can use our trigonometry to relate each of the components x and y back to this vector and the angle. If it's the y component you're interested in, that's going to be your v sine theta. If you're looking at the x, it'll be your v cos theta, and that's straight from your right angle triangle. Okay, so what will we do first? Well, let's go to our list of questions here. Let's start by considering the range. That's a really common one, and what we're going to find is that we are necessarily having to engage with the time. So let's go down that road and see how we get from one question to the next. Okay, so we're going to start looking at the range, which means the x direction. Okay, so I'm just going to make that a little bit bigger. So x direction. So if we think about our kinematic equations and what could be helpful to us, let's start with, well, we've got a delta x equation that's related to velocities. Normally it would be v initial delta t plus 1/2 a delta t squared. Now in this specific case, it's, we can leave it as vi, but we really mean vxi. We're looking only here in the x direction. So vx initial delta t, but then we've got this term with the acceleration. In this case, we're talking about the acceleration in the x, and there is no acceleration in the x, so this is 0. Okay, so let's rewrite this. So we've really got delta x is equal to, now this is Vxi, and we can actually relate that to our actual full velocity vector and the angle. So let's do that. So now we're going to write it instead v cos theta delta t, and that's it, because we eliminated that other term. Okay, so we've almost got an equation for our range, but the problem here is that we've got delta t, and we haven't said anything about that yet. We don't know that. We're also looking for that. So what do? Well, let's go over to the y direction and explore what we can get there. So let's go over to, I'll draw it up here, the y direction. Now we can do the same type of analysis in the y direction, this time looking at, well, it'll be delta y, and that'll be equal to vi delta t plus 1/2 a delta t squared. However, in this case, right, we're being careful, so it's vy initial, so the component of the velocity in the y direction, and this a is the a in the y direction. Okay, so we can do two things here. Let's just rewrite this. So our delta y, and that's our change in our height over this whole motion. Well, we've got the vy, and we can relate that to v sine theta. Going back to this relationship here. Okay, and then we've got delta t, and we've got a plus 1/2. Now the acceleration in the y direction is g, delta t squared. Okay, so now we have our kinematic equation in the y direction. We've substituted in a couple things to make it particular to this situation. Now, because we're dealing with projectile motion along a flat plane, along a surface, we know that your delta y is equal to 0, because you're going to start in a place, you're going to go up, and you're going to end up back at the same y value. Okay, so in that case, we set this equal to 0, the sine theta delta t plus 1/2 g delta t squared. And that allows us to do something very helpful, which is we can divide out one of the delta t's. So if we divide all of the terms by delta t, this goes away, and the square goes away. All right. So that then gives us a much simpler expression. So we've got 0 is equal to v sine theta plus 1/2 g delta t. And that we can now rearrange. So we're going to bring that term 1/2 g delta t over to the other side. And so we're going to have 1/2 g, so this is negative 1/2 g delta t. Just going to separate this out, and that'll be equal to v sine theta. And I just want to isolate delta t. So delta t is now going to be equal to, bring that 2 up here, 2v sine theta over g. Now we got a negative sign there. Okay, so now that's looking quite useful. And in fact, it's so useful, I'm going to put a little box around it. Come on, box. Yeah. Okay, so we've got our nice little box around our expression, and that is going to give us our t. Now, we can go back to what we were doing, can take this and substitute it in and continue on looking at our range. But let's pause here for a moment so that we can look at instead the time. So we'll look at the time first, and then we'll go back and talk about the range because of this link. Okay, so I just want to pull off to the side for a moment. And we're going to make this smaller. We're just going to zoom into this equation. And we're going to talk a little bit about this. So notice a couple of things about this relationship. So delta t. So we were interested, well, how do these three cases compare to one another? How does the angle affect the time? Well, delta t is going to be proportional to, well, 1 over g. So that will mean that if you have less gravity, you're going to have more time in the air. If you have more gravity, you're going to have less time in the air. So I'll zoom in even more. So, on the moon, for example, on the moon, you have less hang time. Okay. Now, the other part to this is, well, what else? Delta t is also going to be proportional to v. So if you have more velocity, you're going to have more velocity in the y direction in an absolute sense. And so more velocity in the y direction means more time in the air. And then finally, we've got delta t is proportional to sine theta. Well, that's an interesting one. And if we think about that a little bit, well, when is sine theta maximum, giving us the maximum amount of time? Well, sine theta is max. And what's the maximum value of sine theta? 1. Sine theta is going to range between 0 and 1. Sine of 0 is 0, and sine of 90 degrees is 1. So sine is max, or 1, when theta is 90 degrees. Therefore, okay, so what does that mean for this? So therefore, let's now consider our three cases. So we've got a projectile at 75 degrees, 45 degrees, and 30 degrees. How would we rank those based on this equation for the amount of time in the air? So we've got a case where we've got delta y, and that's 75 degrees. And then we've got our case for delta y, that's 45 degrees. And finally, delta y for 30 degrees. Well, they're in fact going to be in that order. The larger the angle, from 0 to 90, the more time you're going to have in the air. So that's at a conceptual level. We could try just picking a number for the velocity and actually look at a few concrete numbers. Okay. Let's just try that. Okay. So let's just do an example. And we'll pick something easy. We'll just say velocity is 10 meters per second. And what we're going to do is just copy this equation. Copy. And we're just going to do it 3 times. one for each one of these and see which ones. And we're going to now have an actual value associated with them. Okay. And you know what? I'm going to actually go through and actually color code them so that we're really clear which one we're talking about. It doesn't take but a moment. And okay, everything is what it ought to be. Okay, so in the orange case, the angle there is 75. Maybe I'm going to back that up and make that a little bit smaller. Okay, so we got a sine of 75 degrees, and our G is 9.8. Now, okay, there was a minus sign there, but of course I was also substituting in minus 9.81 meters per second squared, so the two minus signs cancel. Okay, and then my velocity, need a little more space there, 10 meters per second. Okay, and then I got delta t. You put that in your calculator and we get 2 seconds. Okay, so in the case where we've got a 75-degree angle and this 10 meter per second launch speed, we plug it in, we get a hang time of 2 seconds. Okay. So what about where our angle is 45 degrees? Well, our G is the same, 9.81 meters per second squared. Our velocity is the same. And so our delta t here, substitute these numbers, we get 1.4 seconds. Okay, so we are less than we were at the larger angle. Okay, one more and then we're done. We are now at 30 degrees. Same G. And same velocity. Okay. And so our delta t there is 1 second. I'm keeping 2 significant digits just for simplicity, and also reflecting that the angle has 2 digits. 10 is an exact value. I'm interpreting that as having 2 significant digits. Okay, so there we go. That backs up our conceptual understanding and our kind of quantitative. This was conceptual, but it was also, we understood the relationships between these quantities, so we rank them according to the equation and just confirm with some numbers. Okay, so that is our second question. First, what is the time that this is going to take depending on the angle here? So that was our first question. But we thought, well, let's do the range, knowing that we're going to have to deal with time. So now that we've done that, we can go back and now we can deal with the range. And so what we're going to do is go back to our analysis in the x direction and now substitute in our work on time. Okay, so we can substitute that in, carrying on with the range. So delta x is equal to v cos theta, and then we're going to have 2v sine theta all over negative g. Okay. We can simplify this expression a little bit. Let's bring the 2 out front. V squared sine theta cos theta all over negative g. All right, we got one more thing that we can do here, and you're going to see why it's pretty useful in a moment. and that is to identify two sine theta, cos theta as being a trigonometric identity. So you can use a trig identity, which is 2 sine theta cos theta is equal to sine 2 theta. Okay. And maybe just to, yeah, I'll leave that. It'll be fine. Okay, so we're going to rearrange this delta x, or our range, is going to then be a v squared sine 2 theta divided by negative g. And that is our range equation. Now, it depends, how you see it. I mean, here we've got a negative sign. You will see it without the negative sign. And the reason that we have that in this specific case is because of the way I defined g. I said for our purposes, g is going to, in fact, like the letter g represents a negative number. So in this case, that's its form. So this is the range equation. Now let's do the same type of thought process. I'm going to try and separate this out a little bit. Same type of thought process with this equation we did before. So note that our range is proportional to our v squared. So that makes sense. More velocity, more x component velocity, meaning more range. Also significant, more velocity also gives you more time because you've got more velocity in the y direction. So for both of those reasons, we get more range with more velocity. Okay. Also, delta x proportional to 1 over g. And so again, similar to the y direction, if you have more gravity pulling down, then you're going to have less range. If you have less gravity pulling you down, you're going to have more range. So you're going to go farther on the moon than you will on Earth or Jupiter. Finally, delta x is proportional to sine 2 theta. Now, here's where that gets interesting. Okay. Where is sine 2 theta maximum? Okay. So let's just make a little note here. Sine 2 theta is max when the angle is equal to 45 degrees. Because when theta is 45 degrees, 2 times 45 is 90, so sine 90 is equal to 1. So this equation, if you're talking about keeping the velocity the same, the planet the same, so the same g, this equation tells you the range is maximum when the angle is 45 degrees. If you go to a steeper angle, you get less range because more of that component is in the y direction. And if you go to a shallower range, you're going to get less range because you're going to have not enough time in the air to go across more distance. Okay, so as before, let's do a quick example. Okay, so example. And we're going to keep the example number the same. Let's say v is equal to 10 meters per second. And then take a look at what's going to happen here. Okay. As before, I'm going to copy this and make it a wee bit smaller. Okay. And let's just duplicate. And we're going to do it 3 times. Okay. And we're going to quickly code everything so that's easy to see what's going on, what we're comparing. We got blue, we got orange, and we've got green. Okay. So first up, orange. What's going on with orange? Orange is 75 degrees. And we've got a G of 9.81 meters per second squared. And we've got a V of 10. Okay, so in that case, what is our range? We get 5.1 meters. Now, in the case of blue, blue is our 45 degree case. And we have the same velocity, 10 meters per second, and same G, 9.81 meters per second squared. Okay, in this case, delta x, or our range, gives us 10 meters. So almost double. Now, one last one to do. In this case, we are looking at 30 degrees, same velocity, same G, and so we get a delta x of 8.8 meters. Okay, so we have this mapping out what sort of range we get for different angles, and that answers for us that question for the range. So we've looked at the time where we saw that clear relationship with more of your y component. So a steeper angle gives you more time. Now we then looked at the range, and we discovered, well, the range is interesting because overall 45 degrees gives you the most. It's maximum there. And now we can consider that last one. What about the maximum height? And for the maximum height, we're going to have to approach things slightly differently. Like these two were really linked, as we saw. Let's think about the maximum height, though. Now, kind of drawn out this, general projectile motion pattern where we launch it, goes through this nice arc, and ends up, at the same y position. And maybe, in fact, I should. I'll just extend this out a bit, just so that we get that full arc. Okay. We land kind of there. Okay. So when we're considering the max height, I've denoted that with our, this spot here. So we go up to some maximum, and then we go back down. And right away, if you think about doing the exact same type of motion, where you're just throwing something up, in a straight above you, up to some maximum point where it gets to zero, so it goes up, reaches zero, comes back down. That is very much what we're looking at here. So we're going to be looking at the motion just from this initial V to this final V of 0 meters per second at this height. Okay, so to do that, we're going to use a different kinematic equation. We want something without time, so we're going to use V final squared is equal to V initial squared plus 2. It's usually A delta S, where this could be X or D or whatever. Okay, so we're going to use this kinematic equation, and in our specific case, what we're talking about is V YF squared is equal to Vyi squared plus 2G delta y. So that's our application of that with this specific context. Now our final velocity here is 0, right? Right there. So we're going up to some height where that's 0. So that helps a little bit. So we'll say that 0. Our y component of that velocity is going to be v sine theta. And then we've got our 2g. And you know what? In this case, so that it's distinct from other delta y's where we're talking about, we talked about the case where we're going from this initial to that final, and that's still a delta y. I'm going to call it h because it's a particular value representing that height. Okay, so there, well, let's move that term here over to the other side. So we have negative 2gh is equal to, well, we can kind of go v squared sine theta squared. Now we can isolate h, which is what we were interested in. And so h is equal to v squared sine theta squared over negative 2g. And reminding ourselves that g, the way we've defined it, is negative 9.81 meters per second squared. And so that is a very useful equation. Let's draw a little box around it. Keep it neat and tidy. Okay. So now we've got an equation for our height. And in fact, I'm just going to move it down just a little bit, keep things kind of organized. Okay, so now we can take a look and inspect this equation and understand it a little bit more. So just to note about this equation, I guess I'll move this up a little bit. Okay, so note here that our height that we reach is going to be proportional to our velocity squared. Well, that makes sense, right? The more we have velocity, the more we'll have velocity in the y direction, and so the more height we're going to get. Height is also proportional to 1 over g, so stronger gravity, that means we'll have less height. Weaker gravity, we'll have more height. Okay? And then lastly, we have the height is also proportional to sine theta squared. Okay, well, let's unpack that just a moment. This means, right, this one, well, sine theta is max at theta is equal to 90 degrees. So h is max at theta is equal to 90 degrees. Assuming everything else is equal, but that's, we're setting up this equation to understand h. And so if we're considering different cases, which we are, of the angle, 90 degrees is where you get the most. And so if you were to then rank the three cases that we have, which were 75, 45, and 30, well, we would have h, or 75 degrees, is going to be greater than our h for 45 degrees, and that will be still greater than our h for 30 degrees. Okay. As we did before, we can also take an example and say, well, why don't we just use our 10 meters per second example and examine what kind of heights we're going to get here. So let's just take this. I hope it grabs it all. Maybe just a little smaller. Okay, so we're going to have 1, we're going to have 2, and we're going to have 3, and they're going to just fit. Just a little bit more room. Okay. Okay, so let's get into then our colors. Okay, so style is going to be our orange case, and that's going to be our blue case, and we're going to be in our green case. Okay, so we're going to try this 3 different ways, see how the results compare. We're going to start with our orange case, where we've got an angle of 75 degrees. Okay, so sine, maybe we go a little thicker. Okay, so sine 75 degrees, and that is going to be, G is 9.81 meters per second squared. Our velocity here is 10 meters per second squared, and so our height is going to be equal to, oh, sorry, no more negative sign. There's two. Remember, G was defined in our case. We're using negative 9.81 to represent the downwards, so the negative sign went away. Okay, so then we get 4.8 meters. Okay, let's try now for the blue case, where we've got 45 degrees. We've got the same G value, negative 9.8 meters per second squared, and we've got the same velocity, 10 meters per second. Okay, our height then, 2.5 meters. All right, now what about our final case? So we've got an angle here of 30 degrees and a velocity of 10 meters per second, and our G of negative 9.81 meters per second squared. And that's going to give us a height of 1.3 meters. Okay, so we have, again in our example, where we've got the largest height at our largest angle and downwards from there. And that's consistent with our earlier conceptual semi-quantitative discussion here, and our understanding of the equation. Okay, so now we have answered our initial 3 questions, where we've wanted to explore projectile motion and compare these 3 cases where we've got time, range, and the maximum height that they've all reached. And along the way, we've noticed how we have a relationship between the angle and the time and the vertical and horizontal distances, and how the x direction and the y direction are linked through time. Okay.